Well, hello everyone. Today's notes are on something called vectors, and if you've ever seen the movie Despicable Me, you have heard of vectors before. If you've ever taken physics, you've worked with vectors before, but in Despicable Me, there's a bad guy, and his name is Vector, and at one point in the movie, he actually describes where the name comes from. He says it's a mathematical term, and here's what he says. I'll give you a direct quote from the movie. He says, vector is a quantity represented by an arrow with both direction and magnitude. So he gives a perfect mathematical definition of a vector. So here's how we write a vector. So a vector, we put kind of this half arrow above two letters. So this would be vector PQ. And it's kind of like a geometry. Remember back in geometry you learned about rays and segments? It's kind of like a ray and a segment put together. Here's what I mean by that. A ray would go forever. A segment would go between P and Q and stop. So if we have, for example, if I have point P and point Q, segment PQ just looks like this. Ray PQ goes forever. Vector PQ is like a segment in that it has this length from P to Q, but it's like a ray in that it has direction. It starts at P and goes to Q. So this would be vector PQ. P is what's called the initial point, and Q is what's called the terminal point. So vector PQ is this segment going from P to Q, except it starts at P and ends at Q. So in a sense, it's like a segment, sense it's like a ray. It's got direction. This one's going up at about 10 degrees. And magnitude, meaning the length of this, maybe in this case 5 inches. Okay, now component form of a vector, we might say a component form looks like this. And I'll just give you an example. So we use these squared off brackets, not parentheses. So if I have a vector, let's say 6, 4, that means this vector goes 6 units in the x direction and 4 units in the y direction. Okay, so this vector here, not knowing where it starts, but it's going to go 6 units to the right, 4 units up. Here is this vector. Okay. Now, if you ever see this notation, these little, it kind of looks like an absolute value, but it's 2 of these. This stands for the magnitude of that vector, or the length of that vector. Now, the nice thing is, if we know this information, we can use the Pythagorean theorem to find the magnitude. Now, if that magnitude equals 1, then this vector is called a unit vector. And we'll get into that in just a bit. So let's jump into our first example. Find the component form and magnitude of vector v. It starts at this point, 5, negative 3, ends at this point, negative 1, 6. So the first thing I like to do is just make a rough sketch of this, and I would recommend you make a rough sketch as well. So let's see here. This starts 1, 2, 3, 4, 5, and negative 3. So here's where it starts, and it ends at negative 1, 1, 2, 3, 4, 5, 6. It ends up here. So here's this vector. Well, if we had to figure out the component form, we have to figure out how many steps left and right, how many steps up and down. Well, if I count there, I can see it goes 6 steps to the left, and it goes 9 steps up. So in component form, there it is, negative 6, 9. Now, once you get good at this, you realize you can subtract these numbers to get these values, but just be careful because people mess up their signs when they subtract all the time. Okay, so knowing this is negative 6 units, this is 9 units, we can now find the magnitude of that vector by using the Pythagorean theorem. So that magnitude is negative 6 squared plus 9 squared, and then we take the square root of that amount. So it's going to be the square root of 36 plus 81, or the square root of 117. Now leaving your answer as a square root is perfectly fine. We could simplify that. That's actually, this is 9 times 13, so I could say 3 times the square root of 13, or I could write it as a decimal if I choose, but any of those answers would be okay. Now there are some properties of these vectors. So let's say we have two different vectors, and I just call the first one u, the second one v. If we ever add vectors together, we can just add the component parts. So basically this is saying I can add the x coordinates, comma, add the y coordinates. And if you ever multiply a vector by a constant number, or what's called a scalar, it's called a scalar because it's like a scale factor, we can just multiply the different components, the different parts, by that scale factor. Okay, so that gets us into our next example. Actually, this is example 2, my apologies. So let's say we're given these two vectors. Let's figure out each of these. So let's first do this algebraically. Algebraically, this is the easiest way to do this. Algebraically, that just means let's multiply vector v by 2. And if you do that, you get negative 8 comma 6. That's all it is. It's that simple. Graphically, here's how you would do that. You'd say, okay, here's vector v. It goes 4 left and 3 up. Let's start it at the origin. Let's draw vector v in here. If we double that vector, so if I take that vector and double it, draw it over here again, what's the total length of that vector? Well, the total length of that vector would be what we get here, negative 8 comma 6. So you can show that graphically, or you can show that algebraically. Once again, it's easier to do it algebraically, but it can also be done graphically. V plus W means let's add these component parts. So let's add the x's first. If we add those, we get negative 2. Let's add the y's. If we do that, we get 8. That's it. There's your entire vector. Now, how do you show that graphically? Well, vector v would be 4 left and 3 up. So I'm going to get vector v in here again. Now, vector w, from that terminal point, from that end point, we go 2 right and 1, 2, 3, 4, 5 up. So vector w would look something like this. Those vectors put together would give you this final component vector, which goes 2 left and 8 up, which is what we got here algebraically. So much easier to do it algebraically, but yes, it can be done graphically as well. Okay, v plus 2w, that means we'll double this one and then add it to v. So I think we can take care of that algebraically here. That'll give it 0, comma, let's see here, double this, add it up there, 0, comma 13. And again, over here we can say, let's go v, then 2 of these w's. W minus v, well, if you ever subtract a vector graphically, it just means go in the other direction. Okay. If we are subtracting here, we can simply subtract the x and y quantities. W minus v will give us 6, comma 2. Algebraically, much easier to do than graphically, but they can all be done either way. Okay, let's continue. Now, don't write all these down. Actually, these properties are on page 428, and most of these properties are pretty intuitive. This is saying, hey, if we add two vectors, you could add them in any order. Or if you add 0 to a vector, you get what you started with. Now, none of these are real groundbreaking, so don't worry about writing them down. But there is something that you should write down, and it's this down here. Now, I mentioned before unit vectors. A unit vector is a vector of magnitude 1, a vector that's 1 unit long. To find a unit vector, we take the component form of the vector and divide by its magnitude. And our next example is going to ask us to do that. So let's jump right in and try that out. Oh, before we get to that example, I'm sorry, forgot this part here. Standard unit vectors, sometimes we use the letters I and J to represent standard unit vectors. I do not like this notation simply because I think of as our imaginary number. But if you ever see I, this means the vector that is 1 unit to the right. So this is vector I. J would be 1 unit up. So you can take any vector like this and write it in terms of I and j. So 5, negative 3 would be 5 units to the right minus 3 units up. Now, again, I do not like this notation, but you will see it sometimes. So I'm just making you aware of this notation. Okay, so now that we've got that out of the way, let's get back to that unit vector problem. Find a unit vector in the direction of this. And again, I'm just going to make a rough sketch. This vector goes 3 to the right, 8 down. So it looks something like, looks something like this. There's our vector v. Now, vector v, I don't know how long it is. It's definitely not 1 unit long. We want to find the vector that goes in the same direction that is 1 unit long. It's going to look something like this. Well, to find that, here's what we do. We need to find the length of v and divide each of these quantities by that length. So first thing we have to do, let's find the magnitude of vector v. And we can do that with the Pythagorean theorem. So the magnitude of vector v is 3 squared plus negative 8 squared, and then the square root of all that. So the square root of 9 plus 64, which is the square root of 73. Okay, so to find the unit vector, I'll write it out here. Unit vector we can take those two quantities up above. So we can start with that 3, negative 8, and divide each of those quantities by this distance. And that's it. So unit vector, we take the original quantities, divide by the length of that original vector. And you can simplify these and write them different ways, but this answer is sufficient. Sometimes it's good to get it as a decimal, but it's not a need. Okay, so let's extend that. So now this says find the vector v with the given magnitude and the same direction as vector u. Okay, so I'm just going to make a sketch of vector u. So vector u goes 3 to the right and 3 down. So vector u looks something like this. Now we're not looking for the unit vector now. The unit vector, remember, would be 1 unit long. I'm looking for a vector that's actually 4 units long. I don't know where that will be. Could be anywhere in here. But really to find this, it's really not so bad. We can first start by finding the unit vector. So, well, actually before I do that, I got to find the magnitude of vector u. So the magnitude of vector u is, using the Pythagorean theorem, 3 squared plus negative 3 squared. So that gives me the square root of 9 plus 9, which is the square root of 18, which I can write as 3 times the square root of 2, because that's like 9 times 2. Okay, so now the unit vector. The unit vector is those original dimensions over this magnitude. Which we can simplify, and that's going to be 1 over the square root of 2 and negative 1 over the square root of 2. Now that would be this little vector right here. It's 1 unit long in the same direction. We want a vector that is 4 units long in that same direction. Well, this is the easy part. We found the unit vector. Our new vector v is going to be 4 units long, so I'm just going to multiply those quantities by 4. So vector v would be 4 over the square root of 2 and negative 4 over the square root of 2. Let's get rid of that there. There we go. And I'm going to make sure I write it in this component form, and there's my answer. So if you can find a unit vector, then you can find a vector that's any length, because this distance here, whatever it is, we multiply our unit vector by that, and there's our new dimensions. Okay, let's continue. So how does this relate to the unit circle? Well, I'm just going to make a really rough sketch of unit circle. I'm not going to fill in a whole lot of information here, but On my unit circle, let's say I have some angle here. We know that the x-coordinate is like the cosine of this angle, and the y-coordinate is like the sine. Okay, so each of these points here is the cosine of theta and the sine of theta. Okay, now you think about this. Each of these points is 1 unit away from the origin. That's why it's called the unit circle. So I can also say that a unit vector that starts at that origin is going to be equal to the cosine of theta, whatever that happens to be, and the sine of theta. In fact, to find this angle, let's say we know that. Well, we know tangent is sine over cosine. So I can say the tangent of theta equals that sine of theta over the cosine of theta. And in terms of x and y, we can say the tangent of theta equals y over x. And theta, that's what's called the direction angle. So with these vectors, we can say, like if I go back to this problem here, we could figure out this angle by using trigonometry. Okay, that's this here. So theta is that direction angle. So we're going to see a couple problems where we now need to find that direction angle. So fifth example says find the magnitude and direction angle of this vector. And notice it's given in this terms of I and j. When I see that, I immediately just rewrite it in component form. Now that component form means that this vector goes 2 to the right and 5 down. So it's going to look something like this. So here's vector v. And first thing we know how to do this now, is the magnitude of vector v. We can use the Pythagorean theorem. The Pythagorean theorem tells us that this vector, this magnitude is 2 squared plus negative 5 squared. Take the square root of that, so we get 4 plus 25 square root of 29. So there's your first answer. The magnitude of vector v is the square root of 29. That's this length right here. Now the direction angle is this angle right here, this angle theta. So we've got a vector going the square root of 29 units at an angle of what? We need to find that angle. Well, we know that using SOHCAHTOA here, we could say the tangent of that angle equals opposite over adjacent, negative 5 over 2. And if you take the inverse tangent of that fraction, you'll get theta, the angle, is about negative 68.2 degrees. Meaning, hey, this is going down 68 degrees, vector is going square root of 29 units from there. So there's your magnitude and direction angle. Now careful with that. Direction angle doesn't always give us what we're looking for. So make sure this angle matches up with the diagram. Sometimes, if you just type it in your calculator, you'll get an angle that might be over here, which is fine, but really not what we're looking for. We're looking for this angle going downwards. You might have to subtract whatever you find from 180 to find what you're looking for. Okay, one last example. Last example, find the component form. So this is the exact same as the previous problem, but it's the opposite problem. So this is saying now we've got a vector that is 4 units long at an angle of 20 degrees. We need to find these missing coordinates. This one here, this one here. Well, if you know your trigonometry, this one's not so bad. We can say, hey, we know that the cosine of 20 degrees equals x over 4. And if we multiply both sides by 4, we can type that in our calculator. 4 times the cosine of 20 degrees equals x. So x is about 3.8. Same thing to find y, but now we're going to say the sine of 20 degrees equals y over 4. And if you multiply both sides by 4, type that in your calculator, you'll get y is about 1.4. So your component form, we could say this vector goes 3.8 units to the right, 1.4 units up. All right, that wraps up your notes on this unit kind of a lot of homework, but a lot of different kind of problems. So give these a shot, try these out, let me know what questions you have. And when you're set with this, we'll move on to the next unit.